Ever found yourself pondering over how computers store real numbers? Well, you're in the right place. You see, real numbers, those that include both rational and irrational numbers, are typically stored in computers using a specific representation that allows for finite precision. But why do we need to store real numbers in computers, you ask? Well, they're essential for a plethora of tasks from scientific calculations to graphics rendering. However, there isn't a one-size-fits-all way to store these numbers. The method of storage often depends on factors like precision requirements and computational efficiency. There are two common methods we'll be exploring: the floating point representation and the fixed point representation. Now that we've touched on the basics, let's dive deeper into the methods of storing these real numbers in our computers. First up, we have the floating point representation. Now, when we talk about floating point representation, we're referring to a method that uses a combination of a sign bit, an exponent, and a fractional part to store real numbers. This technique is all about precision, and it comes in two main flavors: single precision and double precision. Single precision uses 32 bits to represent a real number, while double precision uses 64 bits. But what do these bits actually represent? Let's dive into that. In floating point representation, a real number is represented as a combination of a sign bit, an exponent, and a fractional part. The sign bit is just one bit and indicates whether the number is positive or negative. The exponent is a bit more complex. In single precision, the exponent is 8 bits, while in double precision, it's 11 bits. The remaining bits are used for the fractional part, also known as the mantissa or significand. This might seem like a lot to take in, but it's all standardized under the IEEE 754 standard, which is widely used for floating point representation. This standard ensures that floating point numbers are represented consistently across different platforms and systems. Let's take a double precision example to illustrate this. Suppose we have 1 bit for the sign, 11 bits for the exponent, and 52 bits for the mantissa. The number is then represented as -1 raised to the power of the sign, multiplied by 1, fraction, and further multiplied by 2 raised to the power of exponent -1023. This might seem like a mouthful, but it's just a way to adjust the exponent to allow for both positive and negative exponents. Take this bit string for example: 0, followed by 10000000001, followed by a 52-bit long string of 1s and 0s. Here, the sign bit is 0, indicating a positive number. The exponent is 10000000001, which translates to a biased exponent of 1025. And the mantissa is the long string of 1s and 0s, following the exponent. This representation gives us a lot of flexibility in terms of precision and range. We can represent very small numbers, very large numbers, and everything in between, all with a good degree of precision. However, it's worth noting that this precision comes with a cost. Floating point arithmetic can be more complex, and operations may take longer compared to other methods. So that's the floating point representation, a method that's all about precision and range. It's a powerful tool in our computational arsenal, allowing us to accurately represent a vast range of real numbers. But as with any tool, it's important to understand how it works and when to use it. As we'll see in the next segment, there are other ways to represent real numbers, each with their own advantages and trade-offs. So stay tuned. Next, we venture into the realm of the fixed point representation. Now, this is another interesting way of storing real numbers in computers, and it has its own unique characteristics and uses. Imagine a real number as a whole part and a fractional part. It's like the division of a cake, the whole pieces and the crumbs that are left. In fixed point representation, we use a fixed number of bits for the integer part, the whole pieces of the cake, and a fixed number of bits for the fractional part, the crumbs. Let's take an example of a 16-bit fixed point representation. Here we use 8 bits for the integer part and the remaining 8 bits for the fractional part. So we have a number represented as integer fraction, just like you'd have a cake represented as whole pieces crumbs. Now you might be thinking, why would we want to use fixed point representation? Well, one of the main reasons is simplicity. Fixed point arithmetic is simpler than floating point arithmetic. However, this simplicity does come with a cost. One of the limitations of fixed-point representation is its fixed precision. Unlike floating-point representation, which can adjust the precision based on the exponent, fixed-point representation has a fixed precision. This means that it can be more accurate for some numbers, but less accurate for others. Another limitation is its range. Fixed-point representation has a limited range compared to floating-point representation. It can't represent very large or very small numbers as effectively as floating-point can. So, if you're working with a broad range of numbers, fixed point might not be the best choice. But don't discount fixed point representation just yet. Despite these limitations, it has its advantages. For example, it's less likely to introduce rounding errors, which can be a significant issue with floating point representation. Also, fixed point representation can be a good choice for certain applications. For instance, in embedded systems or applications with constrained resources, fixed-point representation might be more suitable. It's all about choosing the right tool for the job. To sum up, fixed-point representation is like the reliable, straightforward cousin of the more complex and flexible floating-point representation. It might not have the same range or variable precision, but it's simpler, less likely to introduce rounding errors, and can be a great choice for certain applications. And that's the fixed-point representation for you. A simpler yet more constrained method of storing real numbers. Now, you might be wondering, how do we choose between these two? It's a good question, and the answer lies in a few key considerations: precision, range, and complexity. Let's start with precision. Floating point representation provides higher precision, which is crucial when dealing with complex calculations or large data sets. It's like having a microscope that allows you to see intricate details. But there's a catch. Floating point can introduce rounding errors due to finite precision. Imagine if that microscope occasionally distorted the image, making it slightly off. On the other hand, fixed point representation has a fixed precision. It might not give you the same level of detail, but it avoids some of the rounding errors, like a reliable magnifying glass. Next up, range. Floating point representation has a larger range, meaning it can handle very large and very small numbers. It's like having a telescope that can see distant galaxies and a microscope that can see tiny atoms. Fixed point representation, however, has a limited range. It's more like a pair of binoculars, good for viewing things at a mid-range distance, but not too far or too close. And then we have complexity. Floating point arithmetic is more complex, and operations may take longer. It's like solving a puzzle with many pieces. It can take a while, but the result is a detailed picture. Fixed-point arithmetic is simpler, but may not be suitable for all applications. It's like a simpler puzzle, quicker to solve, but not as intricate. So, which one to choose? It really depends on what you need. Floating-point representation is commonly used in scientific computing, graphics, and other applications where precision is critical. It's the choice of astronomers and microbiologists, so to speak. On the flip side, fixed-point representation might be favored in embedded systems or applications with constrained resources. It's the tool of hikers and birdwatchers, if you will. Ultimately, the choice between these two depends on what you need for your specific application. Alright, let's recap what we've learned. We dived deep into the world of real numbers and their storage in computers. We discovered that real numbers, encompassing both rational and irrational numbers, are represented with finite precision. We examined two common methods of representation: floating point and fixed point representation. Floating point representation uses a blend of a sign bit, an exponent, and a fractional part. It's seen in two forms: single precision using 32 bits and double precision consuming 64 bits. This method offers higher precision and a wider range, but it's more complex and can introduce rounding errors. On the other hand, fixed-point representation, with a fixed number of bits for the integer and fractional parts, provides a simpler arithmetic, but with a limited range. It may be the go-to in embedded systems or applications with constrained resources. And there you have it, a rundown of how computers store real numbers. Thanks for tuning in, and remember, there's always more to learn in the fascinating world of computing.